Last time we talked about mixtures of a few acids when acids are mixed together, or mixtures of only bases when bases are mixed together. In those reactions, we either the acid was a strong acid where it takes over, or the stronger of the weak acids takes over. Or if both acids happen to be just as contributing to the pH, you had to calculate the overall H3O plus from both weak acids. Similar for the bases. In both of these types, the reactant, one of the reactants, of course, was water. Now we're going to talk about an acid-base reaction where the acid and the base, neither of them is water. So I have an acid which is not water and a base which is not water. And we're going to determine the dominating reaction and the Kr of the reaction. And because remember, if neither the reactant is water, we're not talking about neither Ka nor Kb in this case. We're then also going to look at mixtures of many acids and bases in a form of a question, and that we will look at the theory of that part when I discuss question number 32 in the problem set. Of course, buffers also fits into the idea of mixtures, but that's a whole separate area, and we will discuss it separately in part 3 of the acid-base chapter. Now let's look at an example where I have a mixture of two couples, okay? I have a mixture of couple 1, which is HA with A minus in my solution, and I have a mixture with BH plus with B as my second couple in solution. So in solution, I have B and BH plus, and I have A minus and HA, and I put them on a pKa scale because it will ease up how I determine my reaction. It simplifies it slightly. If I put it on a pKa scale, you guys all know how to do this, or you remember it, and we talked about it a little bit on the first chapter, that we put the lowest pKa on the bottom and the highest pKa as we go up. And of course, here the HA with the lowest pKa will be my strongest acid, and the strongest base will be on my left upper right-hand corner. That would be my strongest base because pKa2 here would be my weaker acid and therefore the stronger its base. And the rule says that we should go according to gamma rule, which is the strongest acid reacting with the strongest base. So who's the strongest base? Voila, right there. It's going to react with the strongest acid right here, right-hand corner, and that goes in accordance with gamma. We form a gamma. And so my overall reaction is easily determined once I put everything on a pKa scale, or once I put whoever the strongest acid is on the right hand, at the start, on my left hand here. So HA is my strongest acid, and that should be here, reacting with the strongest base, which is the conjugate of the weaker acid. So my weaker acid would be a product, okay? And the conjugate base of my stronger acid would be a product. Clear? It's very easy when you put it on a pKa scale, automatically they give you the answer, if you will. But it's also easy to just put the strongest acid on the right as a reactant and the weaker acid as a product. And then you could figure out that this will be B and that will be A minus, continuing. Now, another idea. If I already have my reaction given, or if I found what my reaction is, okay? I could also determine what is the Kr for this reaction, because notice in this reaction, I don't have water, so I'm not talking about neither Ka nor Kd. You know, this is acting as an acid, but to be a Ka, if you will, my base has to be water. Okay. So we call this reaction requires a Kr because it's an acid with a base reaction where neither is water. This Kr, of course, is still the same equilibrium type, products divided by reactants, so A minus times BH plus divided by HA times B. That's the expression. So we're going to simplify it further, not simplify it, we have to derive it from somewhere. Okay, I have to get this as a form of numbers. Of course, you can get it if you have the equilibrium concentrations, but you almost never have the equilibrium concentrations. You usually have initial concentrations given. Okay, so let's do a modification slightly. We multiply top and bottom for this reaction, for this Kr, by H3O plus, so it's like multiplying it by 1, so it doesn't affect it. And then put all the couple separated from each other. So HAA minus is separated now from the BH plus B couple. And then take a look at what does this remind you of? This expression right here, yeah, this expression. What does it remind you of? A minus H3O plus divided by HA. Yes, that's like the Ka of HA. What does this remind you of? BH3O plus times B and HB plus. Well, if you flip it, that's actually going to be the Ka of HB plus, or this is actually 1 divided by the Ka of the HB plus. Great, so that Kr is simply the Ka of HA, which is Ka1, they called it that, and divided by the Ka of the BH plus, which is Ka2. Done, great. So I have the Kas for both acids, and I can easily then calculate the Kr. And just so you know, this always hits. If you go to a reaction and you look at the reaction as written, so as written, the Kr for as written, look at the acid on the reactant side, and you say then the Kr is the Ka of the acid on the reactant side divided by the Ka of the acid on the product side. And that always is correct. Let me just go through, because sometimes we can easily get an expression with a pKa. It also really helps. Take the log of both sides of this expression right there. Take log. So this will be log Kr equals log Ka1 and then minus log Ka2. Okay. What is the minus log Ka2? That is pKa2. And log Ka1 is actually minus pKa1. Take the antilog of this, that means that Kr is 10 to the power pKa2 minus pKa1, which is, we consider this pKa2 minus pKa1, or pKa of the product minus the pKa of the reactant as the change in pKa values, product minus reactant. And so 10 to the change in pKa is also equal to the Kr. And so you really don't have to do all this, though I will do it in the examples that are going to come in your problem set, but you don't really have to. We can get the Kr directly by applying this type of equation. Now, if the Kr if we have a slight change in pKa values, you will see that the Kr increases or decreases very, very quickly. The Kr, if you find it and it's greater than 10 to the 4, You already know this number. Again, this is a four species system of the type 1 to 1 to 1. And we actually derived in the first chapter the derivation of, remember, Kr, if it's greater than 10 to the 4, we called it quantitative. And if it's greater than 10 to the 6, we called it complete. And how did we get it? We used alpha when alpha was 0.99 or 99% complete, that we called the reaction quantitative, and 0.999, we called it complete. Now we could have really done that derivation here, but you know, anyways, it's a derivation which you already have. Regardless, I want you to get to the point to it, and that is, if I find a Kr for a certain reaction, and that Kr is greater than 10 to the 4, then you will say this reaction is quantitative, but it's treated as complete. So the reaction is treated as if it is a complete reaction, and then you just do stoichiometry of the reactant and product. You see who's in excess and who's limiting, and you continue from there. In the case where the Kr is greater than 1, and in other words, that the Ka is greater than Ka2, Ka1 is greater than Ka2. And in other words, that this is a stronger acid. The reactant acid is the stronger acid. And in other words, that the reaction goes according to gamma rule. Then the reaction is actually advanced, and it goes in the forward direction. And indeed, it's spontaneous, and it is in accord to gamma rule. So once I have Kr, I know a lot of things. I know that the reaction is going to go forward. I know it's according to gamma rule. I know that it's spontaneous. So sometimes they ask you questions, does it go forward? Does the reaction proceed in forward direction? And they don't have to tell you find Kr. They just ask you for the direction of the reaction, and you should find the Kr if you're asked for such questions. All right. In the case where actually the HA is a weaker acid than the BH+, and in other words, the Ka1 is less than the Ka2, or pKa1 is greater than pKa2, then automatically the Kr will be less than 1. Here, the reaction does not proceed in the forward direction. It goes in the opposite direction. Doesn't mean that it doesn't proceed, but it goes in the opposite direction. Why am I saying that? Because again, we have here a mixture. I actually have initial concentrations here and maybe initial of the product. So I can go in the opposite direction. But as written, the reaction is not spontaneous as written. If you find that the Kr is actually less than 10 to the minus 4, then you would say that this reaction is limited and it doesn't proceed at all, or, you know, it doesn't proceed. Of course, if we still have a Kr, which is a 10 to the minus 4, but you have 0 on the product side, you're gonna go in the forward direction no matter how small it is. We're gonna see examples of this. Great. Let us now apply this idea of Kr and actually finding the K reaction for different species and different reactants. Okay. Okay. So CH3COOH, acetic acid with ammonia. I'm going to go directly here. I'm going to put both acid-base couple on a pKa scale. So I am actually given ammonia and acetic acid as a reactant. But what I'm going to do is I'm going to put each of it with its couple on a pKa scale. So that's right there. The ammonia will require ammonium, and the acetic acid will become CH3COO- as a base in its couple. Put the pKa's on the scale as well. The ammonia here, the ammonium is the weaker acid, has a higher pKa. The acetic acid is a stronger acid. So if we actually look at it, and let me just go here for a moment, look at this arrow. The ammonia is reacting with this acid. And is this according to gamma rule? Yes, it is. There, with that, continue it, you get gamma. And so automatically, this is the stronger base, upper, lower right hand. So if this arrow kind of thing goes like that, okay, you are according to gamma rule. And so will this reaction proceed? Yes, it will. And is it according to gamma rule? Yes, it is. But that didn't really tell me anything. It didn't really, I mean, it did, but I didn't get any data. Data means I need a KR, an actual KR, because then I can see, I could do a calculation of the exact concentration of species in solution. So how do I get a KR? Remember, KR, I can get it just by knowing the pKa's of the product and the reactant, or the reactant and product. So KR, remember, is 10 to the change in pKa value. What is the change in pKa? It's product pKa minus reactant pKa. So in this case, it will be pKa2 minus pKa1, which is 9.25 minus 4.75, which is a number of 4.5. Look at this change in pKa. It's greater than 4. And that means, indeed, my reaction is quantitative and thus treated as complete in doing calculations. My KR, look, it's 10 to the 4.5, yani 10 greater than 10 to the 4, as well the idea of being complete, quantitative, treated as complete in reactions. Next equation, that one in green, okay? We have C6H5OH. This is phenol, benzene with OH, with acetate, CH2 minus. Okay, so let's go and put these guys as a couple on a scale. So here is my phenol, and I'm gonna make him into a phenoxide as a base. And my acetic acid is already on my scale from the previous equation. Great, so what is my, where is my reaction? It's actually that with this, okay? Ooh. Okay, so here's my base. I start at my base going upward like that. Base up. So I'm going up here, okay? And so this is anti-gamma, or if you will, this is that with that. This is, and so I'm not in accordance to gamma rule here. It's going to be opposite to gamma. It's going to be, here's my base going up like that. So anti-gamma. Some people see anti-gamma as this way. This is like that, and the arrow is on the opposite side. Doesn't really matter how you see it. I could have seen it actually before even writing it on a pKa scale, because I would have done the following. Put the pKa underneath each of the acids. So I put the pKa of this acid and the pKa here. And I asked myself, who's the stronger acid? Yes, this is it. It has a lower pKa. So will the reaction proceed? No, because this is my stronger acid. It's on the product side. It should be on the reactant side. So this reaction will not proceed spontaneously, at least. Let's get the K reaction, shall we? That's even easier to do. K reaction is, what's the change in pKa values? Change in pKa is product pKa minus reactant pKa. So that is 4.75 minus 9.9, which is a minus 5.15, which is actually less than -4. Not only does the reaction not proceed, the reaction is actually limited. It doesn't, nearly no reaction in the forward direction. Not only is it not spontaneous, there's hardly any reaction going forward, because look at the KR. It's 10 to the minus 5.15, which is less than 10 to the minus 4. The third question, okay, I'm just going to look at it here, and for a moment I'm not going to look at the pKa scale, okay? So here I have PO4 3 minus ammonium. So of course here I look at these two. Oh, this should be my acid because it has protons. This guy doesn't even have a proton. So he's going to donate a proton to the H3PO4. This becomes HPO4. he's going to donate a proton to the PO4 3 minus. This becomes HPO4 2 minus, and I donated a proton, so it became ammonia. So already I got my equation here without actually putting on a pKa scale. And then I'm going to put underneath the acid pKa, the pKa of the acid. So this is 9.2 and 9.25. pKa of this acid is 12.4. I look at the pKa values. Who's the lower pKa? Oh, it's right here. So this is my stronger acid. My reaction is going to be spontaneous because my stronger acid is my reactant. Okay. Of course, let's get a Kr for this reaction. It's change in 10 to the change in pKa, which is 12.4 minus 9.25, which happens to be 3.15. So my K reaction is 10 to the 3.15. Of course, this is spontaneous in the forward direction, but it is not quantitative, okay? It's not quantitative nor complete. Therefore, what do I have to do to get calculations at, of each of the species at equilibrium? I have to do an actual equilibrium calculation and get what X is and solve it. Remember, when the change in pKa is between -4 and 4, that means that I have to do an equilibrium reaction, okay? That's when I have to do an equilibrium to do any type of calculation. Now, just looking here, going back, just look. Here is my PO4 with my NH4. Indeed, this is in accordance to gamma. That's my stronger base, stronger than the ammonia. And this is my stronger acid. This is stronger than the HPO4 2 minus. That being said, you are responsible, please, to solve the following questions. Question 38, that's a mixture of two acids. Number 12, determining Kr and which reaction takes place. Number 13, that's a weak acid and a weak base mixture. Number 14 is two acid-base couples where we're given the concentration of the acids and the bases in the couple. And the hardest question which I find in the whole course of this course is question number 32. Give it a shot, try to solve it. We're gonna have a recording of the solutions for these as soon as I can. Just briefly, I'm gonna need this part. I usually derive it when I get to buffers because that's when this equation is actually used. It's called the Henderson-Hasselbalch equation. But I'm gonna do it here right now because remember how I kind of stopped myself from deriving for you the ampholytic pH equals half pKa1 plus pKa2. I said I will derive it later, and usually I derive this after I discuss buffers. But I'm gonna derive it right now, okay? I'm not gonna derive that right now, but I'm gonna show you something that I will need to do the derivation of such questions. Well, this is very simple. I could have even done it at the beginning, but because we don't use it until we get into buffers a lot, I prefer to discuss it at the buffer stage. Nonetheless, okay. If I have an acid, HA with water becomes H3O plus and A minus, you all know that the Ka of such an acid will be A minus H3O plus with HA in the denominator, where the concentrations here are the concentrations at equilibrium, right? Great. Now, the unfortunate part, why we don't use this, is usually I don't have the concentration of A minus at equilibrium, right? So we have to find it through X, and we used to put X and C0 minus X and solve for the X. Now let's do this type of derivatization here. Take the log of both sides of this equation. So this is going to be log of Ka equals a log of H plus, but keep this coupled together. So log of H of A minus divided by HA. So I kept this together. Now, why did I do that? No particular reason, because we're doing this type of derivation. Now, take the log of h plus, put him on the other side, and the log of Ka, put him on the other side, and then take the, what will that be? This will be minus log of H3O plus, which is simply the pH, and this will be the minus log of Ka on this side, which is pKa. And this is the equation that I actually need. I need pH equals pKa plus log of A minus divided by HA. If and only if I have the concentration of A minus at equilibrium and I have the concentration of HA at equilibrium, then indeed I will have the pKa, I could get pH. So if you have A minus and HA in solution, both species are present, I can use this equation to calculate pH. Clear? Okay, so this becomes nice when you have both A minus and HA, and we're going to see this when we do the derivation of some acid-base couples, or when we actually calculate maybe the A minus and HA concentration at equilibrium. Then we can use this to get pH, and you will see as I do some problem solving when I use this equation. Okay, we call this the Henderson-Hasselbalch equation. You will see it a lot more in buffers. I love it in buffers. Very helpful. Great. Enjoy the problem set. Don't forget your homework. There it is. And try it out. Okay. I will keep you posted to when the solutions will be online.